Great. Thanks, Josh. So Jess's name is underlined here because I'm mostly going to talk about some work from her PhD. She's supervised by Dave, Jeff, and I, and so when I say we did something, mostly I mean Jess did it with the advice from the rest of us. It was hopefully occasionally useful. So I think everyone in this room knows that marine protected areas are not always used as a fisheries management tool, but they're almost always implemented in places where fisheries exist, and so they'll have implications for fisheries dynamics. And for that reason, people are interested both in the short-term impacts of establishing no-take marine protected areas, but also long-term consequences for yields and populations subject to fishing. When we study transient effects, typically the sort of data that we collect would be things like biomass as a function of time since protection of the fish in the sea, catches, and so forth. And the models we use to draw inferences from those data are typically descriptive formulas that are meant to characterize trends. So for example, is biomass going up or down after we set up no-take areas? Are yields increasing or decreasing? When we attempt to evaluate long-term effects, we typically don't have long-term time series of things like biomass and catch. Normally, the models we use rather than descriptive trend lines are some sort of population projection model. So this is a classic or matrix projection model. So you basically say, well, what are the abundances of fish of different ages or sizes? And then what are the contributions that individuals make to future population size based on how old or how big they are now? So the data we use for these sorts of models will typically be information about those demographic contributions. So how big is a fish of a certain age, and how much of a contribution to, say, reproductive output does that fish make? Now, there are advantages and disadvantages of both of these approaches. So when we study transient effects, one of the great things about it is that we're actually directly measuring the quantities of interest. So we want to know about the health of the population. We want to know what the yields are. And so we are looking at that explicitly. Disadvantage is that typically we're using descriptive models, and so that complicates drawing some of the inferences we might be interested in, such as what's the long-run effect? Just if yields decline in the short term, does that mean yields will be lower in the long term, or will they recover? And also, typically when we implement protected area, no-take protected areas, we do other stuff as well, either in a management sense or in terms of other things happening in the environment. And so drawing inferences about what is actually causing the responses can be problematic. For long-term effects, well, one advantage is because we use demographic models, it's somewhat easier to attribute projected changes to different causes. That is, what changes occurred because we set fishing mortality to 0 in the no-take habitats. We can explore what would have happened under alternative scenarios. Disadvantage is that we typically calibrate the model with data, but we rarely evaluate the sufficiency of the model structure. So functional relationships involved in demographic rates often involve some uncertainty, and commonly those things can't be tested explicitly. So what Jess is trying to do here is actually leverage some of the benefits of both of these approaches. Okay, as a case study, Jess decided to look at coral trout on the Great Barrier Reef. One reason for that, as most of you know, the Great Barrier Reef was rezoned around 2004, and associated with that, coincident with that rezoning, there was a big decrease in fishing effort on the Great Barrier Reef and also in catch. On the outer barrier, where the commercial fishery is, where most of the fishing pressure comes from, there were also changes to coral trout biomass, as biomass increased, particularly in areas that had been newly designated as no-take. Now, earlier this year, Fletcher and colleagues wrote a paper where they said, well, our analysis of these changes in the fishery before and after these closures don't support the claims that people like me and other people made that these closures would not have a really big effect on yields. And then they go on to say the catch and catch rate from line fishing haven't gotten better over time either. So you said these effects would be small and wouldn't last that long, but actually they're big and they're ongoing. Now, several people in this room, myself included, were involved in a response led by Terry making the point that there was also substantial fisheries restructure that occurred around this time, and that's likely to have a lot to do with why why catch went down so much. So what Jess wanted to do is say, well, can we actually estimate the relative contributions of the restructure of the fishery and the expansion of no-take areas to changes both in what happened with the fishery and also what happened with the abundances of coral trout on the reef? And then can we project the long-term implications for yields of this combined strategy relative to 3 alternative scenarios? What would have happened if we basically left things as they were before 2004? What would have happened if we had only done the rezoning, hadn't restructured the fishery, and what would have happened if we had done the opposite? So the question is, yes, catches went down, but in the short term, and is that short-term decline inconsistent with higher yields in the long run or not? So the model that Jess used was a spatial matrix population model. So the model has age structure, so fish are small when they're young, and then they get bigger as they get older, and they progress to those older size classes if they survive. They also mature from juvenile to adult. The adults produce offspring, which can survive and become part of the next population of 1-year-olds. Recruitment is density dependent. That just means the more established biomass there is of coral trout, the harder it is for the incoming larvae to get a foothold in the population. Coral trout change sex from female to male, so we include sex change. The males contribute to population growth by providing sperm, which lead to enhanced fertilization of eggs and therefore more larvae. There's also spatial structure, so the fish either live in fished or no-take habitats. In fished habitats, obviously, they're subject to fishing mortality as well as natural mortality, and these populations are demographically connected through dispersal of larvae across reserve boundaries. Okay, the data that's used to calibrate the model were a bunch of data collected by lots of people in this room of things like growth rates, mortality, essentially demographic rates for coral trout, mainly on the Great Barrier Reef. Estimates of dispersal, exchange of larvae between no-take and fished habitats came from this relatively limited data, but the data that we have comes again from people in this room, which come from parentage analysis. The relationship between fishing effort as recorded in the fisheries data and the actual mortality experienced by coral trout was inferred based on historical data on fishing effort prior to 2004 and the fact that coral trout abundances seem to be approximately constant over the decade before the rezoning. This thing in yellow is the thing we know the least about. That is, how likely is it that a spawned egg turns into a 1-year-old next year? And so that relationship was constrained to a plausible range of boundaries based mainly on estimates of unfished population sizes. If you set fishing mortality to 0 in the model, does fish biomass level out roughly where it should level out for a population that's not fished? Oversimplifying a bit, but I can talk to you about it at the tea break if you want. So, okay, the points on this graph are reported data. The top 2 graphs are fisheries data. The bottom graphs are a biomass of coral trout in fished and reserve offshore habitats from recent Emsley et al. Paper. And then the bottom right is a weighted average, that is fished and reserve abundances weighted by their relative prevalence on the reef. The dotted line, is simply a backward-looking moving average, so it's sort of smoothing some of the fluctuations in the observations. In 2009, Cyclone Hamish went marauding down the Great Barrier Reef, doing lots of damage, and you can see effects both in the catch rate and the fish abundance data, as well as in things like coral cover, and Cyclone Yazi as well. Whoops. Cyclone Yazi then, a couple of years later, did a bunch of damage as well. The purple line is what Jess's metapopulation model predicts. Now, bear in mind, there's no fitting here. The data on the graph are not used in the model calibration. And so I just want to draw your attention to the fact that this steady increase in catch rates after the rezoning is pretty well captured by Jess's model. Obviously, the model doesn't know when cyclones are going to occur, so once Cyclone Hamish hits and hammers the reef, then there's quite a divergence between the data and the model. The model does a pretty good job of capturing in the top right this big decrease in catch, and then the slow recovery after that, although overestimates the drop a little bit. It captures what's happening in the fish zones a little bit. The main things it's not getting, firstly, it hasn't got the magnitude of that drop right, as I mentioned, and secondly, it's somewhat underestimating the increase in biomass in the reserves. Okay, so the next question is, so the model's more or less capturing the short-term dynamics reasonably well. The question is, what happens if you only did a fisheries restructure, if you only did rezoning? And so that's what this shows. The horizontal line at 1 is essentially the projection for what if we had done nothing. The green is reserves only. The orange is the reduced effort only. And so what you can, so a couple of main points here. One is that almost all of the initial decrease in catch is driven by the fisheries restructure, the reduction in effort. What the rezoning does is somewhat slow the rate of recovery in catch. Second point I want to make, and I think this is not fully appreciated, the sensitivity analysis suggests that the fisheries restructure actually has a lot to do with the recovery of coral trout biomass on the reef. That's independent of the rezoning. And that was not expected. So all we've done here is just stretch out the time horizon from 10 years to 100 so that you can see where biomass is going. A couple of main points. One is that all 3 of the scenarios outperform the business as usual in the long run. So those short-term declines in catch and so forth are perfectly consistent with long-run benefits. The restructure without the rezoning produces the highest catch rates in catch. The orange line is on top, whereas the combined strategy produces somewhat higher overall abundances. Now, I mentioned that for density dependence, we had to constrain parameter estimates to a range of values, and so that's what this is meant to show. So this band is actually that reflects the degree of uncertainty. And the magnitude, so what I mean by insurance cost of reserves is basically the distance between the orange and the purple. That's the lower yields that you get because you've set up protected areas. The magnitude of that cost is very different. If you look at the tops of the envelopes, the difference is about 15% or so. If you look at the bottoms of the envelopes, you can sort of see the lighter purple before the orange is behind it. The difference is actually very, very small, negligibly small. And that sensitivity is driven by uncertainty about the strength of that density-dependent recruitment component of the model. And so I want to talk a little bit about that. So the general question, of course, is what's going to happen to a fishery when you spatially structure your fishing effort? And normally we just think in terms of what I'm calling the lockup effect, which is like, okay, if we take 1/3 of the habitat and we don't allow fishing and there's no demographic connection between the populations, you just reduced your fish population by 2/3, and so the productivity is reduced, potential productivity is reduced by 2/3 as well. That effect goes away the more dispersal connection there is between habitats. And we know from work by Jeff Jones and colleagues, including lots of students and research fellows in this room, that this lockup effect is actually fairly small on the Great Barrier Reef. Second is something called Jensen's inequality. And Jensen's inequality has to do with what happens when one thing is a nonlinear function of another thing. So what's relevant? Why is that relevant here? Well, if you think about coral trout as a bunch of populations on different reefs, different reefs throughout the GBR. Each of those populations makes some contribution to overall growth of the metapopulation. That depends on the amount of biomass, right? Larger populations will make different contributions than smaller populations, and that contribution will be nonlinear in some way. So what's Jensen's inequality? Well, imagine first that we have a system where we're fishing the same everywhere, and so everybody's close to the average biomass. The contribution that each population makes to the overall productivity of the system is that blue dot there. What we do if we set up no-take areas is we induce spatial variation in abundance by fishing not at all in some places, and a little bit harder in other places. So take the idealized case where we do that in such a way that the average biomass stays the same. So now the reserve populations are making the contribution of the red dot on the right, the fish populations, the red dot on the left. The key point that's relevant to, and the reason Jensen's inequality is important, is the average of those contributions is not the same as the contribution at the average abundance. And that difference drives a lot of the discrepancy or the differences in yields and population productivity that comes from spatially structuring fishing effort. Okay, so if you look at coral trout, it turns out, although there are lots of nonlinearities in determining population fecundity, size-fecundity relationships are nonlinear, age-size relationships are nonlinear, it turns out that the relationship between population biomass of coral trout and the overall production of eggs is pretty close to linear, so there's a very limited nonlinear averaging effect for egg production. But once those eggs are produced, they then have to be fertilized. And fertilization success is a strongly nonlinear function of biomass. Biomass is small. For something like coral trout that changes sex, you're fishing really hard, so very few individuals survive to be male. And so that means you don't have very many sperm to fertilize the available eggs. So every male you add gives you a substantial increase in fertilization success. The curve increases steeply. If you have a larger biomass, you've got plenty of sperm, and so adding another male doesn't make much difference, doesn't increase fertilization success. So so in this case, spatial variation in abundance induced by spatially structured fishing effort is going to reduce average fertilization success. Conversely, those eggs, once they're fertilized, they have to come into a habitat and establish themselves where there are a bunch of resident adults around that are running around looking for something to eat. Recruitment success tends to be a different nonlinear shaped function of population biomass. The more adults there are, the lower your chance of successfully recruiting, and obviously that's going to asymptote towards zero because you can't have a negative recruitment success. So density-dependent recruitment actually causes a population's productivity to increase when you spatially structure fishing effort and induce variation in abundances. And so the reserve models that produce higher yields with reserves than without them, typically models that have very, very strong density-dependent recruitment. But in general, it is the trade-offs of those different nonlinear responses, those effects on productivity, that will determine whether yields are higher or lower, or how much lower when you implement no-take reserves. Okay, so several points I want to make. One I think I forgot to put on this slide is that the reductions in catch that are seen over the short term on the GBR are perfectly consistent with long-run yield enhancement relative to the business as usual scenario. That's what all of those simulations suggest. Also a fairly simple marine reserve metapopulation model for coral trout captures those transient trends in catch rates and abundance of coral trout on the Great Barrier Reef. There's a tendency for the model to slightly overestimate the cost to fisheries and to underestimate the recovery of biomass in marine protected areas. Declines in catch and increases in the abundance of coral trout from 2004 onwards are substantially attributable to fisheries restructure, actually more so than the rezoning in the sensitivity analysis. And that's a bit of a surprise, at least with respect to biomass recovery. Projected long-run yields with the combined strategy are substantially higher than under that business as usual scenario, but they are slightly lower than projections with restructure only. So you can think of this as a sort of the insurance premium that you're paying to have the habitat and biodiversity protection of a no-take marine area. And Jensen's inequality is a key to understanding that insurance cost relative to conventional fisheries management. The reason why emphasizing this is because calibrating these nonlinearities is something almost nobody is doing, but it is hugely important to understanding how fish populations will respond to rezoning. I think there are two reasons for this. One is that we don't make marine biologists learn enough mathematics, so they don't know about Jensen's inequality. Not surprised that I'm going to say that. The other reason, of course, is that collecting these kinds of data are very hard, much like estimating dispersal of larvae from one patch to the other. And so often these estimates will come with huge amounts of uncertainty. But the point is, even a small amount of additional information about these parts of the life cycle has a huge payoff in terms of our ability to anticipate what might happen relative to getting more information about size-fecundity relationships, or stuff we already know a lot about. That's it. Thanks very much.